In our daily life, we come across various kinds of motions. Motion of an object can be broadly categorized into two types, repetitive or non-repetitive. If an object makes repeated motion after a fixed interval of time, it is called periodic motion. Some examples of periodic motion are rocking a cradle, rotational motion of hands of a clock, a pendulum, etc. Time required for the object to complete one complete oscillation is called period, which is expressed in seconds. Number of oscillations the object makes in a second is called frequency, which is expressed in hertz. A simple harmonic motion is characterized by the object moving in one dimension, oscillates back and forth about a fixed mean position. The object is always acted upon by a force that points towards equilibrium position, and magnitude of force is proportional to displacement of the object from the mean position. In a simple harmonic motion, the displacement or the position of the object is expressed from its equilibrium position by the equation x of t equal to a cos omega t plus pi, where a is the amplitude or the maximum displacement of the object from the mean position. Omega is angular frequency, pi is the initial phase angle, and t is the time. Note that omega is expressed in radians per second, which is equal to 2 pi by t, where t is the time period in seconds. Let us consider the displacement as x of t equal to a sin omega t plus phi, velocity equals dx by dt, and acceleration equals d2x by dt square. We get acceleration equal to minus omega square x. The equation of motion for a simple harmonic motion can be derived using Newton's law, force equal to mass into acceleration. So d2x by dt square equal to minus omega square x, which is a differential equation of second order. The solution for this differential equation is in the form x of t equal to a sin omega t plus phi, which represents a sinusoidal motion with amplitude a and angular frequency omega. The maximum distance the object moves from the mean position is called amplitude. In the equation, a is the amplitude. The number of oscillations the object makes in 1 second is called the frequency. For a spring mass system with mass m and spring stiffness constant k, frequency equals 2 pi square root of k by m. The phase angle represents the initial condition of the object when the motion starts. It can be taken as 0, assuming the sinusoidal waveform of the motion starts from mean position with a 0 phase angle. The diagram shows graphical representation of the motion of the object for one complete cycle. Plus a is the amplitude of the motion on one side of the mean position, and minus a is the amplitude on the other side of the mean position. The diagram shows the velocity of the object for one complete cycle. Note that the velocity is zero at both extremes, whereas it is maximum at the equilibrium position. Maximum velocity is given by angular frequency multiplied by amplitude. Similarly, the acceleration is minimum at equilibrium position and maximum at extreme points. The magnitude of acceleration is 0 at mean position, and at extreme positions it is equal to omega square a. The expression for kinetic energy in a simple harmonic motion can be derived from Newton's formula kinetic energy equals half mv square, where m is the mass of the object and v is the velocity. You will notice that at equilibrium position, the kinetic energy is maximum and its magnitude is given by half k a square, where k is the spring constant and a is the amplitude, and at the extreme positions, kinetic energy is equal to 0. The force exerted by the spring at mean position is 0, and at the extreme positions it is equal to minus k times x. Naturally, the potential energy due to spring is 0 at the mean position and maximum at extreme positions. We have considered zero loss simple harmonic motion. The maximum kinetic energy should be equal to maximum potential energy, assuming zero energy loss in the system. Let us consider a classic example of spring mass system in which the mass slides over an ideal frictionless surface. If m is the mass and k is the spring constant, period t equal to 2 pi square root of m by k. If the mass is suspended by a spring, the spring gets stretched downward by an amount equivalent to mg by k. So the main position gets vertically down by this much amount. The properties of oscillation like frequency do not change. If there are two springs of constant k1 and k2 connected in series, one end of the series firmly fixed and an object of mass m is suspended from the other end, let d equal to distance stretched due to the weight of the mass and k equal to equivalent spring constant d equal to mg by k. The first spring gets stretched by mg by k1 and the second spring gets stretched by mg by k2, and the sum of mg by k1 and mg by k2 equals mg by k, where k is the equivalent spring constant. Therefore, mg by k equals mg by k1 plus mg by k2. You will get equivalent spring constant k equals k1 into k2 divided by k1 plus k2. If two springs of constants k1 and k2 are combined in parallel, the entire weight mg is balanced by both the springs. The force equal to mg equal to k times d, where d is the stretch of the composite spring system. The total force equals force on the first spring plus force on the second spring. So k times d equals k1 times d plus k2 times d. Therefore, equivalent spring constant k equals k1 plus k2. Another classic example of simple harmonic motion is a pendulum. An object of mass m is suspended by a string of length L and the system oscillates due to gravity g. It can be mathematically proved that the period of oscillation t is equal to 2 pi square root of L by g. Longer the string, longer the period. Note that the period and hence the frequency is independent of the mass of the oscillating object. We shall take some examples for study. In the first example, average human heartbeat rate is 75 per minute. Calculate the frequency and period. Given is 75 beats per minute, which is mathematically equivalent to frequency of 75 beats per minute. We have to calculate the beats per second, which is equal to 75 divided by 60, equal to 1.25 beats per second. Period of each beat equal to reciprocal of the frequency, which is equal to 1 divided by 1.25, equal to 0.8 seconds. In the second example, which of the following functions of time represent simple harmonic function, periodic but not simple harmonic, and give the period for each case? The first function is sine of omega t minus cos of omega t, which can be simplified and expressed as a sinusoidal function root of 2 sine of omega t minus pi by 4. This is a simple harmonic function with period equals 2 pi by omega and phase angle equals to minus pi by 4. The second function is also a periodic function having period t equal to pi by omega. It is a harmonic function with a point of equilibrium occurring at half instead of 0. In the example 3, a body oscillates with a simple harmonic motion according to equation x equals 5 cos 2 pi t plus pi by 4. You are asked to calculate displacement, speed and acceleration of the body at t equal to 1.5 second. To calculate the displacement, use the displacement formula and substitute t equal to 1.5 seconds in the equation. To calculate the speed, get the derivative of the function and substitute t equal to 1.5 second. To get acceleration, find the derivative of the speed function and substitute t equal to 1.5 second. In the example 4, a mass of 1 kg is suspended from a spring of stiffness constant 50 Newton per meter. If the block is pulled 10 centimeters from the mean position, calculate the kinetic and potential energy and total energy when the mass is 5 centimeters away from the mean position. To solve this example, we have to get the velocity equation and we have to calculate the time when the mass reaches 5 centimeters away from the mean position. Given values are x equal to 0.1 meter. Using mass and stiffness of spring constant, calculate omega. Using the position formula, calculate sin of omega t and also cos of omega t. In the velocity equation, substitute x equals 0.1 meters to calculate value of velocity. Calculate kinetic energy using equation half mv square and potential energy using half kx square. At the maximum displacement, kinetic energy is 0 and potential energy is maximum, and that is the total energy of the simple harmonic motion. Potential energy at extreme displacement of 10 cm is calculated using the equation half kx square, where x is equal to 10 cm. In the example 5, use the time period equation of simple pendulum t equal to 2 pi square root of L by g. From this equation, L equal to gt square divided by 4 pi square, you will get t equal to 2 seconds. From the equation, length of the pendulum equals 1 meter. Exercise 1 and 2 are for practice. The solution for each exercise is given. Please pause the video and go through the solution provided. We have reached the end of the video. Thank you for watching.